Okay, so good afternoon, class. In this class, I plan to solve some problems. Okay, so based on the Tanzaghi's bearing capacity theory. Okay, so let's go to this one note here. So I have already typed some problems here. Okay, so let us try to solve these. So all of you can see my this whiteboard. Please respond.
Yes, sir.
Whether
Yes.
all of you can see my whiteboard. Okay, thank you. Wait a minute. Yeah. So take down this problem. Uh, so try to solve along with me. Okay. So don't sit idle. Huh? So try to solve along with me so that you can. It will be you can appreciate that. Huh? Okay. So what they are telling a 2 meter wide strip foundation they are telling. Okay. So it's a strip foundation. That's one important point out you have to do that. Okay. So it's a strip foundation. Is placed at a depth of 1.5 meter within a sandy clay where the cohesion is 10 kilonewton per meter square and angle of internal friction is 26 degree, and your gamma is 19 kilonewton per cubic meter. Okay. So determine the maximum wall load that can be allowed on the foundation with a factor of safety of 3, assuming the general shear failure case, and use gross values. Okay. So they given these NC is equal to was the given NC 27.09, so 27.09, and NQ is equal to 14.21, and N gamma is equal to 9.84. Okay, so these are the given data. Okay, so first let me draw a foundation here. So strip foundation. Yeah. So what's the width of this foundation? The width is 2 meter. And so this may be my ground level. Okay, so this is my ground level, and what is the depth of foundation they are telling? The depth of foundation is 1.5 meter. Okay, so this is depth of foundation. Okay, so D is equal to 1.5 meter. Okay, and what are the parameters they given? It's a sandy clay they told. Okay, so the soil is sandy clay. Okay, so what are the parameters they given of the sandy clay? Cohesion they given around 10 kilonewton per meter square, and phi value they give phi value they given how much? 26 degree. Okay, and the bulk density. Okay, so bulk unit weight gamma they given around 19 kilonewton per meter cube. Okay, so they are not talking about anywhere the water table is the details about water table is they're not given. That means there is no water table at all. Okay, so that means the water table is not going to affect the my bearing capacity of this foundation. Okay, so they are asking you to assume it as a general shear case. Okay, and also what is the general for the general shear case? What is the formula for this Tanzaghi's bearing capacity equation? That is Q ultimate is equal to CNC plus QNQ plus 0.5. Why it is 0.5? Because they are telling strip footing. Okay, so if it is a square, then 0.4. If it is a circle, then it is a 0.3. Okay, since it is a strip footing, it's a 0.5. C and C, Q and Q plus 0.5 gamma B n gamma. Okay, so anyway, NC, NQ, n gamma they given in the problem itself. Okay, so simply substitute, you will get the answer. Okay, so what is Q ultimate? Q ultimate, what is C value? C is 10 kilonewton per meter square. Okay, so 10 into, what is NC? NC is 27.09. Okay, so this is my first term. Plus, what is second term? Second term is Q into NQ. What is Q? Q is nothing but gamma times your depth of foundation. Okay, so gamma is how much? Your unit weight of soil, 19 into the depth of foundation is 1.5 meter. So this together is my Q value. Okay, into NQ. NQ is how much? 14.21. 14.21 plus, what is my third term? Third term is 0.5 into gamma. Gamma is 19 into width of foundation is 2 meter. Okay, so 2 into your n gamma. How much n gamma? N gamma is 9.84. 9.84. Tell me. How much?
862.84.
So Q ultimate is equal to how much? 862.8.
Yes, sir.
862.8. Very good. Kilo Newton per meter square. Okay. So this is the ultimate load. Okay. So what is the allowable load? So Q allowable is equal to Q ultimate divided by factor of safety. So factor of safety they given 3. Okay, so 862.8 divided by my factor of safety. See, if you apply this much load now on this foundation, if you apply 862.8 kilonewton per meter square, then it is going to fail this foundation. That's why I have to reduce this by applying some factor of safety. Okay, so I will assume factor of safety of 3. Okay, that's what Q allowable means, the allowable load applied on the foundation. Okay, so this is the ultimate load. So at this load, the foundation is going to fail. So you don't want a failed foundation, right, for your structure. Always you should, the foundation should not fail. So that means you have to apply load lesser than this much. So what is the allowable load? Q allowable is nothing but your ultimate load divided by factor of safety. So factor of safety usually it will be assumed as a 3. So how much you are getting? So around 287. 287.6 kilonewton per meter square. Okay, so this is my Q allowable. So this is the intensity. Okay, so this small Q allowable is what? Kilonewton per meter square it is. Okay, so they are asking you to calculate what they are asking you to calculate. Determine the maximum wall load that can be allowed. Okay, so how much load they are asking. Okay, so this is nothing but if you multiply this quantity with your cross section area of your foundation, then you will get Q allowable. Okay, so my Q allowable, that is capital Q allowable, is equal to your small q allowable into what? The area of your foundation. Okay, so this is nothing but 287.6 into what is the width of foundation? Width of foundation is 2 meter. And length, length is infinite. Okay, so wall length will be very high. Okay, so for per meter run I will calculate. Okay, so that means I will multiply by 1 here. So this will give me kilonewton per meter run. Okay, so tell me how much you are getting. What is the Q allowable? How much?
575.2.
575.2.
575 kilonewton. Yes. Yeah, 2 3 I will leave it. Okay, 575 I will write. Okay, so 575 kilonewton per meter run. Okay, so this is my answer. So this much load you can apply on this wall. Okay. Let me write here. How much gamma they give? Gamma I will write here. Gamma is equal to 19 kilonewton per meter cube. Okay. Any doubt here? Simply, it's a simple substitution. Okay, so nothing much, not a big deal it is. Okay. So just you have to remember the equation for the stiff footing. Suppose if it is a square footing, then what are the changes going to happen here? Here 1.3 will come, and here it will come 0.4. If it is a circular footing, then here 1.3 CNC and 0.3 gamma B and gamma. Okay, that is the only difference. Okay, depending on the shape. Okay, so let us see this problem. Second problem. So this problem, what they are telling, a design requires placing square foundation. They are telling. Okay, so it's a square foundation at 1 meter depth to carry a column load of 1,500 kilonewton. 1,500 kilonewton. The soil properties are C dash and they given, phi dash they given, and gamma they given. What should be the width B of the foundation? Okay, so what they are asking, they given all the soil parameters, and they given what type of foundation they want, and at what depth they are putting, and what load they are asking, putting on that column. So you need to give the dimensions. Okay, so for this dimension, for this much load, this much dimension is can be placed in the field. Okay, so that like that you can answer him. Okay, so let first draw the figure here. Okay. So how much load they are putting on this one, on this column? This Q is equal to 1,500 kilonewton. Okay, and it's a square foundation. Design require so placing a square foundation. Okay, so what is the width of foundation? Your B is equal to 1 meter, and your length also, your depth also will be 1 meter. Okay, so it will be like this. Okay. Anyway, this is understood. Okay, so I will remove this. Sorry. Okay. So this is my ground level. So this is the ground level. 1 meter. Sorry. Okay. So this is square foundation at a 1 meter depth. Okay, dimension they not given. They are asking you to give the dimension. What is the breadth and what is your length? Okay, so dimension is in question mark. But they given the depth of foundation is 1 meter. Okay, so here the depth of foundation is 1 meter. So, and soil properties they given. Okay, so what are the soil properties they given? C is equal to 15 kilonewton per meter square, and phi is equal to 24 degree, and gamma is equal to 18.5 kilonewton per meter cube. Okay, and the given for this phi value of 24 degree, your NC is equal to 22 23.36 23.36. Okay, and NQ is equal to 11.40. So these values will be given in the examination. Okay, so don't worry how I'm getting these. Okay, so they will give you in the problem statement itself. Okay, so since I not typed here, I am writing here. Okay, so n is equal to 23. NQ 11.40 and n gamma is equal to 7.08. So what should be the width of foundation they are asking? Okay, so for the square footing, what is the Q ultimate? That is your 1.3 CNC plus QNQ plus 0.4 gamma B n gamma. Okay, so this is the equation for the square footing for from Terzaghi's bearing capacity theory. Okay, so they are asking you to find out this. This is question mark. These I don't know the width of foundation. I don't know. Let it put it as a question mark itself. Okay. Okay. So what are the parameters I know? I will put it now. So Q ultimate is equal to 1.3. What is C? C is 15 kilonewton per meter square. And what is NC? NC is 23.36 plus what is Q? Q is nothing but gamma times your depth of footing. Gamma is how much? 18.5. 18.5 into depth of footing is 1 meter into NQ. NQ is 11.40 plus 0.4 into gamma. Gamma is again 18.5 into B. I don't know. I will keep it as it is. B into N gamma is 7.08. 7.08. Okay. So what is Q ultimate? Tell me. So Q ultimate is equal to. So you should get 6.4 plus. So this together I am telling. Okay. So this term and this term. If you combine both, you will get this term. Plus 0.4 to 18.5 into 7.08. So around 52.4 times your width of footing. Okay. Okay. So now I know the ultimate load. So what is the allowable load? Q allowable. Q allowable is equal to your Q ultimate divided by factor of safety. So how much? This term divided by your factor of safety. Okay, so 52.4B plus 666.4 divided by factor of safety will be 3. Okay, so if you simplify this, you will get so Q allowable is equal to 17.5 times your width of footing plus if you divide 6.4 by 3, if you do that, then you will get 222.1. Okay. So simply 52.4 into B you divide it by 3 and 6.4 you divide it by 3. I will get this. Okay, so simplified. Now, once I get the Q allowable, what is the applied pressure on the ground? Applied pressure is nothing but your whatever load is there, that load divided by area. Okay, will give me the applied pressure. Okay, so the applied pressure to the ground I will get some space here. Okay. So the applied pressure to the ground is nothing but your whatever load you applied here, that is my Q divided by area, will give me the applied pressure on the ground. So 1500 kilonewton is my load. 1500 kilonewton is my load, and let B is my width of foundation. I don't know, still I don't know the width of foundation. Okay, so B is my width of foundation. B into, since it is a square, so your breadth and length both will be same. So B by B. So now, see, whatever this applied pressure should be equal to this this Q allowable. Okay, so I will call this as equation 1, and this as equation 2. Okay, so you both equate both 1 and 2. Okay, because your Q allowable is nothing but whatever from the calculation you are getting, this Q allowable is nothing but your applied pressure itself. Okay, so that's why. So your 1500 divided by B square is equal to 17.5 B, 17.5 B plus 2.1. Again, you simplify this. Okay, so 17.5 B into B square. Okay, so I will get one cubic equation. I will get. Okay, so that cubic equation will be something like this: 17.5 B cube plus triple 2.1 B square, 2.1 B square, then minus 1500 is equal to 0. Okay, so it's a cubic equation. Okay, so like your ax cube plus bx square plus cx plus d is equal to 0. Okay, so this kind of equation it is. So if you see, if you can solve this cubic equation, so you can solve it by your calculator. Okay, so if you have this fx, I think all the calculator is all. Okay, so fx 991. Okay, so if you see, if you go to that more clear in there and you take the equations, in that equation you can you left click and then they will get this what do you call degrees. Okay, so in that degrees it's a third degree equation. So your coefficients, you put the coefficient 17.5 for the first coefficient and triple 2.1 as the second coefficient, and the third coefficient is 0 here, and fourth coefficient anyway it's 1500. If you put you will get 3 roots you will get. So like x1, x2, x3 will get. So do it. You know how to solve this cubic equation? Anybody can solve this cubic equation with your with the help of your calculator. Okay, so in the calculator it's already built-in functions will be there. With that built-in function, we can solve this cubic equation. Like it is same like your quadratic equation. Okay, your like ax square plus bx plus c. How you will solve? No? Like that, it is a cubic equation. So I solved it. So here we will get something around x1 will be 2.384 and x2 will be minus 12.1 and x3 will be not. I will put it in terms of like b1, b2, b3 because here b is there. No? So b1, b2, b3 is equal to minus 2.96. Okay, so these are the negative roots. So I will ignore this negative root. So always your breadth, whatever width will be there, that is some positive number, right? So that's why your width of foundation should be 2.384. Okay. This is your answer. what should be your root of foundation? 2.4 by 4. Okay, it is almost like your 2.4 by 2.4. Understood? Any doubts here in this problem? Hmm? Any doubts here? Hmm? Yeah. So shall I proceed? If you don't have any doubts, then I will proceed further. Okay, so now see, whatever these two problems I solved, I did not consider, I did not see any water table. Okay, so these are very straightforward and easy problems. So without water table they given. Okay, so next what I am going to do, I will solve some problems with the water table. If water table is there, then how your bearing capacity will affect. So that we will see. So in the morning class, I have explained these effect of water table already. Okay. So what I will do, I will recap those things. Just I will brush up your mind with those uh, correction factors. Then I will take this problem. Okay. So this problem is based on the your water table. Okay. So before solving this problem, I want to just brush up your mind with those effect of water table. Okay, so summary of effect of water table. It's say one word only. Okay, so water table. Effect of summary of effect of water table on the bearing capacity. This word is not recognizing this water table. Okay, actually some textbook they will write together water table, right, and some textbook they will write separately. So effect of some okay, so we'll do first there are three cases we have discussed, right? So let me draw first a figure here. Then see, along with me, if you write, then only you will appreciate. Otherwise, if you simply sitting idle, then it's a waste of time for you. Okay. So along with me, you should write it down. Why I am writing? Because already see, I already explained through the PPT. I don't have to write it all, but still I am writing because I want you to be like along with me. You should also practice. So this is your foundation. Okay, so let me draw this the center. Okay, so this is your ground level. And this is your limit. Hmm? This is the ground level. This is my ground level, and this is my width of foundation, and this is my depth of foundation. This is the depth of foundation, and this depth is equal to Okay, so this depth is equal to your width of foundation, that is B. Let me write D only. Okay, so sometimes I will write D and sometimes I will write D suffix F. Okay, don't get confused, both are same only. Okay, now case number 1 I will discuss. Okay, so let me take this case 1. Anyway, case 1 I will discuss with you. So case number 1. What is the case number 1? Can you recall? Please tell me what is the case number 1. If the highest water table is well below the foundation level, that means what? Your water table reduce it. So your water table is somewhere here. Okay, so this is my DW, depth of water table. Okay, so if you have this is your case. Okay, so if you have a depth of water table well below your width of foundation, that is your DW, depth of water table is greater than your D plus B. D, that is depth of footing, plus your depth which is equivalent to your width of foundation. If this is the case, then no correction is required. No correction is required. That means what is the equation? Q ultimate is equal to CNC plus QNQ plus 0.5 gamma B n gamma. As it is, you can use. Okay, so in this Q, what is the Q? Is nothing but gamma times your depth of footing. Okay, so this gamma will be your gamma bulk. This gamma is there now. Gamma bulk into your depth of footing will give me Q value. Okay, but here also your gamma is nothing but your gamma bulk only. So there is no change at all. No correction is required. Okay, now case number 2 I will check. So case number 2. What is the case number 2? In the case number 2, the water table is somewhere here in the summer season, but in the monsoon season, what will happen? This water table may rise and it may come up to here. So from here, that means you are in the second case, the water table is fluctuating from in the range of D region. Okay, so from in this region to in this region, it will fluctuate. So that is my case number 2. Okay, so my case number 1 was the water table is fluctuating from this level downwards. Okay, so let me draw that. Okay, so case 2. So now, if the highest water table is well below the if the water table is at the footing level and may rise to the ground surface, that is my second case number 2. Okay, so let me write here. If the water table is at footing level, if the water table is at footing level, and it may rise to ground level. It may rise to ground level. So that is my second case, number 2. Then what are the changes you can expect? So let me write the original equation. Q ultimate is equal to CNC plus QNQ plus 0.5 gamma BN gamma. Okay, so what are the changes will happen here? Now this Q is there, no? So now you see this Q into NQ is affecting my this soil as well as this soil. Both soil it is affecting. So that's why in the both parameters I should take a submerged unit weight, because let's see, once the water table is rise up to ground level, what will happen? This soil will lose some weight. Okay, because it is in the submerged condition. Okay, as well as this soil also will lose some weight. Okay, so that's why I have to take the submerged unit weight, or gamma dash I should take in this calculation. Okay, so your Q can be calculated as Q is equal to your gamma dash into your depth of footing. So what is gamma dash? Gamma dash is nothing but gamma saturated minus your unit weight of water into D will give me this term. Then what is the change will happen in this term here? Here your gamma, now it becomes gamma dash, that is gamma sat minus gamma W. Okay, so saturated unit weight minus unit weight of water. So these are the two changes will happen in your case number 2. Okay, so now we'll see case number 3. Okay, so in the case number 3, what is going to happen? So the water table is here. In the summer, in the monsoon season, the water table is here. Then in summer, what will happen? This water table will reduce and it will fluctuate in this depth. Okay, from here to here. So it may come up to here. From here, it may reduce and it may come up to here. Okay, so in this region, if the water table is present in this region, then that will be my third case. Okay, at that time, what will happen? What is my third case? Tell me. So third case is if the groundwater is at the footing level and may fluctuate between footing level and depth equal to the width of footing. So if the groundwater table is at a footing level, and may fluctuate between footing level and depth equal to width of footing. Okay, that means in this region if the water table is saturated, then what are the changes will happen to my equation? Let me write my original equation. Q ultimate equal to CNC plus QNQ plus 0.5 gamma B N gamma. Okay, so this term is not going to change. No change at all for this term. No change. No change in this term, because this second term is what? Second term is in contributed by the soil present above the footing. Okay, so your water table is fluctuating in this region. Okay, so this soil is not at all affected by the fluctuation of the water table. So you have to take as it is. So there is no need to apply any changes here. But this soil is that is my third term. Okay, so in the third term the water will affect the my unit weight. Okay, so that's why this is this gamma. So this gamma now will become gamma dash. That is gamma sat minus gamma w into 1 minus dw minus d divided by t. Okay, you see, so my gamma dash now I have to take the submerged unit weight. Okay, so but submerged unit weight it is the weighted submerged unit weight. Okay, so that means, see, suppose my water table is exactly at the footing level. Then what will happen? My dw is equal to d. So my dw equal to d. Then what will happen to this equation? Suppose water table is exactly at footing level. And what will happen to this equation? Gamma dash equal to gamma sat minus gamma w into 1 minus. Now my dw is equal to d. Okay, so dw minus d will get cancelled because both are same quantity. Okay, so it will become 0. So this term will become 0. So ultimately you left with gamma sat minus gamma w. Suppose this water table now, if it is exactly at b level, exactly at this level, if the water table is exactly at this level, then what will happen? My dw is equal to what? D plus b. My dw is equal to d plus b. Now you put in this equation, what will happen? Suppose water table is exactly the footing level. Okay, so what will happen? My d equal to dw. So d is equal to dw. Okay, they will get cancelled. So 1 minus 0. Yeah, correct. Now here, what will happen if you put your dw is equal to d plus b? What will happen? You see now, gamma dash is equal to gamma sat minus gamma w into 1 minus your dw is now what happened? D plus b minus d divided by b. So dd will get cancelled and the b also will get cancelled. It will become 1. 1 minus 1 is 0, almost 0. Okay, so that means your gamma dash is nothing but your gamma sat. So this, if water table is exactly at what level? At d plus b level. Understood? So this is the summary of the 3 cases. Okay, so let us go to the problem. Yeah, take the problem. What they are telling. Let's solve this problem. So a 3 meter by 3 meter it's a square footing. Okay, so square footing has to be constructed in sandy layer. Sandy. This is the sandy soil. Okay, so this is sandy soil. Calculate Q ultimate. Okay, so they are asking you to calculate Q ultimate for each condition in the figure. Okay, so they are given this figure, and determine the percentage of reduction of bearing capacity in the final state compared with the initial state. Okay, so they are asking you to calculate 4 cases here. Okay, so one is see, this is the influence zone. Hmm? So this is the influence zone, and case number 1 is if the water table is somewhere here. Hmm? The water table is somewhere here. So this is my case 1. Case number 1. Huh? Then my second case is, this is my case number 2. So that means your water table is in between your from the footing and before your influence zone. Okay, so this is my case number 2. Case 2. The water table is at AA level. Then in the third case 3, the water table is somewhere here above the foundation. Huh? So that means this is my case number. So this is case number 3. Sorry, not this one, not this one, not this one. Here, case number 3, and then this is case number 4. Case number 4. Okay, so that means if the water table is at the on the ground surface. Okay, so let us solve case by case here. So let us start with case number 1. Case number 1. So do you whether any water table correction has to be applied for the case number 1? Tell me. If you look at the problem, any water table correction is needed for the case number 1?
No, sir.
No. Why? Why it is not needed? See, this influence zone is there, no? This influence zone from the footing, this will, how much? What will be the depth? This will be. This is equal to what? 3 meter. Whatever width of foundation. Very good. So whatever width of footing is there, no? So that is 3 meter here. If your water table is beyond this level, then you need not to worry about water table. Okay, so because it is not going to affect. So let us write the case number 1. Okay, so when groundwater table is beyond the influence zone, beyond the influence zone. So what will be this influence zone? Tell me how much. What will be this influence zone? You tell me. So this is 3 meter plus 2 meter. Okay, so that means 2 meter from 2 meter from the ground plus your 3 meter from your footing level. Okay, so 5 meter. If the water table is at a depth of 5 meter, more than 5 meter, if the water table is at a more than 5 meter, then need not apply any correction at all. Okay, so simply you write that equation. So my Q ultimate is equal to CNC plus QNQ plus 0.5 gamma BN gamma. Okay, so I have not written NC, NQ, N gamma values here. Okay, I will write here. So my NC for phi value of 30 degree, NC they given 37.16, NQ 22.46, and N gamma 19.13. Okay, so what is C? How much C is given? Anyway, C is not given. Okay, so this term will be 0. Why it is 0? Because only 5 is there. There is no C. C is 0 here because it's pure sand here. They told it's a pure sand. That's why C will not be there. Cohesion will not be there. Okay, so the first term will become 0, Now tell me Q, how much Q will be? 2 into your bulk unit weight. What is the bulk unit weight they given? Bulk unit weight is 15 kilonewton per meter cube. Okay. So 2 into 15 into my NQ. NQ is how much? 22.46. 22.46 plus 0.5 into again bulk unit weight only I have to take. Okay, so this bulk unit weight how much? 15 kilonewton per meter cube. 15 into width of foundation is how much? 3 meter into n gamma. N gamma is 9.13. Tell me how much you will get. How much? Sorry, here not 0.5. It's what is the shape of the footing they given? It's a square footing. No, then it must be 0.4. Sorry, so this is 0.4. If it is a strip footing, then it is a 0.5. Since it is a square footing, so it is a 0.4. So 0.4. So this is my second term and this is my third term. Okay. So tell me how much answer you are getting? Q ultimate.
1018.14.
1018.14. Huh?
Yes, sir.
Oh, kilopascal. Okay. Okay. Now case 2 we'll discuss. Okay. So case 2 I'll write it with the red mark. So what is the case 2 here? When groundwater table is at AA level. Okay, so this is AA level. AA level. That means just above your influence zone. Then what is the equation? First, let me write the equation. Then I will change. I will write the correction factors. Okay. So I will reduce the size here. So Q ultimate equal to CNC plus QNQ plus 0.4 gamma B N gamma. Okay. So if the water table is at 1 meter from, water table is at 1 meter from the ground level. Sorry, not from the footing level, right? So this much soil is in a dry condition. Okay. Can you see this cursor here? Huh? So do you want me to hide here? I think this much soil. Okay, so this much soil will be in a dry condition. From here, it is in a submerged condition. Okay, so this much I have to take dry weight, and this much I have to take the submerged weight. Understood, no? Okay. So anyway, my first term will be 0 here. Because why it is 0? Because I don't have any C value. Cohesion is 0 here. Okay, so what is the second term here? Second term again, see this second term again, it is not going to affect by this water table by this water table. So by this water table, I'm not this soil is not going to affect. So let me write here equal to. So what is the Q? Q is nothing but the unit depth into unit weight. Okay, so 2 meter is your depth of footing. Yeah, so 2 into your bulk unit weight. I have to take the bulk unit weight because the soil is in the bulk because the water table is much below your footing level. Okay, so 2 into 15 into what is the NQ value? NQ is 22.46. 22.46 plus plus 0.4 gamma. See, now gamma will change here because see, this much soil is in dry condition and this much soil is in wet case. Okay, so I will represent that as a gamma. What I can call gamma double prime. I will put. I will calculate this double prime later. Okay, so gamma double prime I will put into B. What is the B? B is 3 meter into n gamma. N gamma is 9.13. Okay. So now this gamma, I have to take the weighted effective weight. So how to get to that weighted effective weight? You remember that case number in our discussion. What is the case? What is the case of this one? I think it is a third case, right? So if the water table is fluctuating between your footing level and your influence zone, then that is my third case. So for the third case, your how you will calculate this unit weight? Double prime is equal to gamma sat minus gamma w into 1 minus dw minus d divided by what? D. Square bracket. Okay. So what is the gamma saturated? How much I given gamma saturated? You see, gamma saturated is 19 kilonewton per meter cube. Write down here. 19 minus unit weight of water is anyway 9.81. Even you can, some people can take 10 also, no problem. Okay. So into 1 minus depth of water table minus your footing depth divided by width of footing. So what is the depth of water table here? So depth of water table is 2 plus 1, that is 3 meter. So 3 minus your depth of footing. What is the depth of footing here? 2 meter. 2 meter divided by what is the width of footing here? Width of footing is 3 meter. Tell me how much you will get? Gamma double prime.
12.46.
12.46. Very good. 12.46 kilonewton per meter cube. Okay, so now you put this double prime in this equation. Where you put? Tell me the answer. Q ultimate. How much you will get?
$959.8.
Okay, very good. 959.8, which is almost equal to 960 again right now. 960 kilonewton per meter square. Okay, so this is my case number 2. So in the case number 1, how much I got? Okay, now, so third case, in the case number 3 is here, water table is here, right? So I will take a green color here. Okay, so case number 3, this I will discuss now. So case 3. So that means your water table is at 1 meter from your ground level. Let us solve that. Case number 3. So when your groundwater table is at BB level. Where is my BB level? You see, this is my BB level. Okay, so this is my B level. Okay. So if the water table is here, what is the case number? What is my case here? This is your second case. That means if the water table is fluctuating between the footing level and the ground surface. Okay, so in this range, if the water table is varying in this range, that is my second case number 2. Okay, so let us solve the problem here. So what is the equation? Your Q ultimate equal to 1.3 CNC plus QNQ plus 0.4 gamma BN gamma. Okay, so anyway, this is 0 because my cohesion is 0 here. So what is Q here? See, this much soil is dry condition. Okay, so you see from this water table, above that up to 1 meter, it's a dry case. Soil is in dry condition, so I have to take the bulk unit weight. From the 1 meter up to the level of footing, it's a saturated condition. Okay, so there I have to take the submerged unit weight. Okay, so your Q now becomes, so 1 meter, that is a dry unit. So 1 meter is in dry condition. Okay, so that into the bulk unit weight. Bulk unit weight is 15 kilonewton per meter cube. Okay, so plus another 1 meter below the foot from the ground level, from the water table, it's a saturated case. See. So this 1 meter is a dry case, and this 1 meter is a what? This 1 meter is a submerged case. So let us write that. So 1 into 15, and then 1 into your gamma saturated minus unit weight of water. What is the saturated unit weight? Saturated unit weight is 19. 19 minus 9.81. 19 minus 9.81. Okay, into NQ value. What is the NQ? NQ, how much they given? NQ 22.46. So 22.46 plus this one 0.4 into this term. Anyway, it is a submerged case only. Okay, so I have to take the submerged unit weight. 19 minus 9.81 into your width of foundation. Width is how much? 3 meter. Into N gamma. N gamma is how much? So N gamma is 19.13. 19.13. Tell me how Q ultimate.
$3,307.
How much? Sorry?
3,307.
3,000. 1 meter, 1 into 15. No. Anybody else? Any other answer is there?
1194.
I think I am getting not 1194. Let me calculate myself. So 15 plus 19 minus 9.81 into 22.46 plus 0.4 into 2 I'm getting a 754. 754.644 kilopascal. Anybody is getting this number? Huh?
Yes, sir.
Anybody is getting this number? Please respond. Okay. Okay.
Yes, sir.
So now case number 4. So where is my case number 4? Yeah. So case number 4 is at a CC level, that is at the ground level. Huh? So let me take the blue color. So this thing I will discuss now. Case number 4. Case number 4. That is when groundwater table is at CC level. That means ground surface or ground level. Okay. So let me write the formula here. Q ultimate equal to 1.3 CNC plus QNQ plus 0.4 gamma B N gamma. Okay. So once the water table is here, so once the water table is up to ground level, then entire thing is under submerged condition. All the soil is under submerged condition. That means you have to take the submerged unit weight. So all the gamma should become your submerged unit weight. So let us calculate this. So anyway, this term is 0 because my cohesion is 0. So Q is equal to, what's the depth of T? Depth of T is 2, right? So 2 into weight is 19 kilonewton per meter, right? Let's check it weight. 19 kilonewton per meter. Okay. So 19 minus 9.81 into my NQ. What is the NQ value? NQ value is 22.46. Plus 0.4 into gamma. Again, gamma is now becomes a submerged unit weight. Okay, so that is 19 minus 9.81 into your width of foundation is 3 meter. Into my n gamma is 19.13. Now you calculate your Q ultimate.
It's 23.7.
Sorry,
623.78.
23. I think 610. I'm getting 610.
623, sir.
9.
623, sir.
623. Okay, if it 623. Okay, so I have taken 10 here instead of 9.81. I have taken 10. Okay, anyway, I'll keep 623. So 623 point. 623 point. How much?
78.
78. So it is around 624 kilonewton per meter square or kilopascal. Both of them. Okay. Now all the cases are over. What they are asking you to find out how much bin capacity is reduced. Okay, the bin capacity in the final state compared with the initial state. Asking how much percentage is reduced. See earlier when there was no water table, that is my case number one. So whatever my bin capacity I was getting, admitted bin capacity around 1018 kilopascal, 1018 kilopascal. Now see, if the water table is rising up to the ground level, then it is reduced 621. Okay, so how much it got reduced? Huh? So that is your Q final by Q final divided by Q initial. So final I got 624. 624 kilonewton per meter square. And initially how much I was getting without any water table, if there is no water table. So that is 1018 1018 kilonewton per meter square. Okay, so it is almost 40%.
61%.
Reduction in main capacity. Sorry, 40% is correct, no? 624 by 1018.
61, sir.
Okay, so 61%. 1 minute, I will calculate 624 by 101. Yeah, 61%. So 61%. 61% reduction in the bearing capacity. So you see, almost more than 50%. What will happen? Your bearing capacity will reduce if the water table is comes up to your ground level. So if the water table comes up to this level, then almost 50%, whatever earlier strength was there, that much it will reduce. You see how much important role this water table will play. But in practicals, in practical case, when we are doing some consultancy work, no, so you will not consider all these cases. Okay, always worst case is what? Worst case is at the ground level. So we have to design it for the worst case condition. So always you have to take the water table at the ground level when you are start practicing. Okay, when you start practicing your civil engineering course, at the time whenever you are designing or whenever you are calculating bearing capacity, then always you have to take the water table at the ground surface, because you don't know see the life. What is the lifespan of your RCC structure? Maybe 50 years you take, 40 to 50 years if you take. In that range, one or two times it may come up to the ground level. Your soil, your water table may come up to ground level in that 40 year or whatever lifespan of building is there. No? In that lifespan, at least once or twice, the groundwater table may rise up to your ground level. So always you should consider for the worst case. Here worst case is case number 4. That means your water table is at the ground level. So that is your practical implications. Okay, so always you take whenever you are designing any foundation, you should design it for the water by considering water table at the ground level. Okay, so any doubt regarding this problem? Any doubts are there? Please respond, anybody. No doubts? Yeah, Suresh, are you there? Suresh, Ravindra, anybody, please respond. If you have any doubts, then we will discuss it. Otherwise, I will proceed further. Shall I proceed? Snehalata, Priyadarshini,
No doubt, sir.
no doubts.
No doubts,
Snehalata,
sir.
okay.
No doubts,
So,
sir.
okay. So that problem, I will anyway. That whatever today I solved the problem, no, that I will upload it in the Google Classroom. Okay. So once again, you go through that solution. If you get any doubt in that solution, you can ask me in the tomorrow's class. So before ending this session, I want to just recap IS 6403. I will recap that IS 6403, but at the same time, I will give one homework also. Whatever problem we solved, no, just now with that water table, the same problem now you have to solve using IS 6403. So using IS 6403, you solve it, and let us see how the answers will vary. So I think I should give shape factor, depth factor, and then inclination factors. Okay, so if you use IS 6403, then I should give these factors. Anyway, I will calculate and I will give them. Even if I'm not able to give, you can calculate on yourself also, because anyway, IS 6403 also I will upload it in the Google Classroom today. So you refer to and then you take that equations and calculate shape factors, depth factors, and inclination factors. Anyway, inclination factor will be 0 here. Sorry, 1 year, because the loading will be in the vertical direction. Okay, so you have to calculate only shape factor. You have to calculate, and the depth factor you have to calculate. So then you can proceed with that different position of your water table. Okay, so then you can solve that. Okay. So tomorrow you should tell me the answers for all the 4 cases using IS 6403. Okay, so this is your assignment. Okay, so now I will once again I will recap that IS 6403 so that it will be helpful for you to calculate those whatever assignment problem I have given just now. Okay, so let us go to that IS 6403. Yeah. So the net ultimate bearing capacity, you have to use this equation. In this equation, I see your shape factor and depth factor. You have to calculate from these formulas. Okay, so the given problem is square footing, no? So for the square footing, what are my shape factors here? Okay, see here for square footing, my shape factors, that is SC is equal to 1.3. This SQ is 0.8 and S gamma is 0.6. And I think SC is equal to 1.3, SC, SQ, and S gamma. S gamma for square footing is 0.8. Okay, so SC, SQ, S gamma for square footing 1.3, 1.2, 1.3, 1.2, and S gamma for square footing is 0.8. SC, SQ, S gamma, you know, these things I got. SC, SQ, and S gamma. Now depth factor also I will calculate. Okay, so what are the depth factors here? You see these equation you have to calculate from DC to DQ and D gamma depending on your N5 value. You have to calculate. So anyway, inclination factor will be 1 year. Okay, so IC equal to IQ is equal to I gamma is equal to 1, because you are applying load exactly vertical. For that assignment problem I am talking. and depending on the position of your water table, you have to consider your W dash here. So let us start with the case number 1. What is the case number 1 here? If the water table is likely to permanently remain at or below the depth of which is equal to df plus b beneath the ground level surrounding the footing. Okay, so then at that case W dash will be your 1. Okay, so this water table correction will be one value. Okay, so that means the case number 1 is somewhere like this. Okay, so let me draw a figure here. So this is the case. Okay, so this is the limit of influence. So if the water table is fluctuating from this level downwards, then that is my case number 1. So at that case, your that means what? That means your there is no need of any correction at all. Okay, so no need of any correction. That means your correction factor for the water table is 1 here. Okay, so this is 1, and whatever gamma is there here, that will be your bulk density you should use. And whatever your Q value will calculate, that again it will be bulk density, because so this soil is also not affected by your water table, and this soil is also not affected by your water table. Okay, that's why we are using the bulk unit weights here. Okay. And your water table is your water table correction will be 1. This is nothing but no corrections at all. Now, case number 2. What is the case number 2? If the water table is located at a depth df, that means here. If the water table is located at a depth df, and then it likely to rise to the ground surface. Okay, so it may rise up to ground surface. Okay, in this case, how you will calculate? How you will accommodate these correction factors? See, your W dash is now 0.5. Okay, you see this W dash is now your 0.5, and your gamma is now becomes gamma saturated. So you see earlier in the general case, if you see earlier in our previous discussion, here we have taken gamma dash. Here we have taken what we taken? Gamma dash we taken. Okay, so gamma dash equal to gamma sat minus gamma W. But in IS 6403, what they are telling, they use you use gamma sat only in my third term, but you apply 0.5. This is nothing but same only. See, usually saturated unit weight will be around 20 kilonewton per meter cube. It will be there. Then if you reduce this water table, the unit weight of water, that will be something around 10 kilonewton per meter cube. So that means half is reducing here. Okay, the same thing we are multiplying here. It's like one or say it's other way of representing the this thing, whatever we discussed in our previous problem. The same thing only. See, instead of calculating a submerged unit weight, they are what 6403 is suggesting. You use your saturated unit weight only, but you multiply by 0.5. It is same only. So almost almost here also you are reducing by 50%, right? By taking gamma dash, you are reducing this contribution by 50%. In the same way, here also you are reducing 50% only by multiplying 0.5. Okay, so that's why I am telling both whatever the previous method we discussed and this method almost same only, but the representation is different here. So how it is different here? We are reducing it by 50% by multiplying 0.5. In the earlier case, we are reducing by deducting your unit weight of water, that is almost 10 kilonewton per meter cube. Okay, so in the 20, if you reduce it by 10, almost it is reducing by 50%. Okay, the entire thing is reduced by 50% only. This entire contribution is reduced by 50%. The same thing is holds good even in 6403 also. Okay. Now, so in the second case, what will happen to Q value? Because see, if the water table come up to this level, what will happen? All the soil is under saturated condition. So you have to take here I am taking your submerged unit weight. Here I am taking submerged unit weight into a depth of 40. Anyway, this term is not going to change at all. case number 3. In the case number 3, what is the case number 3? If the water table is somewhere here, so in the monsoon it is somewhere here, but once summer starts, what will happen? It may reduce. It may reduce and it may come up to this level. Then what is the change you have to apply? Okay, so at that case you have to do what? You have to do the linear interpolation between 0.5 and 1. So your W dash is what? Your W dash will vary between 0.5 and 1. And your gamma will become gamma saturated, and your Q will be bulk density into depth of footing. So take these out, these three figures you take. You take a snapshot of these 3 cases, and then you try to solve that problem. So I will allow some time to take the photograph of this thing. Anyway, I will upload this PPT later on. But for time being, to solve that whatever assignment problem I given, you take this photo. You take a one snap. This is case 1, and case 2 you take. This is for case 2. You can take a photograph of this one. And this is case 3. For the case 3, you take the photograph. So all the cases you refer to this these 3 cases, and then try to attempt that assignment problem. Okay. Okay. So are you comfortable with this effect of water table? You want me to solve some more problems? I am ready to do so. If the concept is clear, then I will stop it here. If you want me to solve some more problems based on the effect of water table, then I can do that also. What do you want? You tell me.
Tomorrow, sir.
Tomorrow? Okay.
Yeah.
So yeah, tomorrow I will take up one problem based on the effect of water table. Okay, so that will be my final problem. I will give 1 or 2 days to solve that assignment problem. Okay, so your assignment problem is, see, whatever problem I solved in today's class, the same problem you have to solve using IS 6403. Okay, so I will give 2 to 3 days. I won't expect you to solve by tomorrow. Maybe by this weekend. Okay, maybe by next Monday. By next Monday, I will ask you to give the answers for those assignment problem. That is your assignment problem for your for as far as your unit 4 is concerned. Okay, so I will stop it here.
Yes.